Good evening, everyone, and a very warm welcome to all the delegates and honored guests present today. On behalf of the organizing committee, I would like to welcome you all to the second online technical session on AIoT, Embedded ML, and Tiny ML workshop, conducted as part of the SLIoT Challenge 2026. As most of you might already know, SLIoT is Sri Lanka's premier annual IoT challenge open to school students, university undergraduates, and to all other innovators across the country. This is organized by the Department of Computer Science and Engineering, University of Montreal, in collaboration with SLT Mobitel and IESL, which is the Institute of Engineers, Sri Lanka. We are pleased to announce that due to the overwhelming interest and enthusiasm shown, the registration deadline for SLIoT Challenge 2026 has been extended until 2nd February 2026. We strongly encourage anyone who has not yet registered to take advantage of this extended deadline and be a part of this exciting national challenge. With introductions out of the way, let's move on to our speaker of the day. It is my greatest pleasure to invite Mr. Ishara Niranjana, Senior Machine Learning Engineer at Zone 24/7. He has over 3 years of experience with building and deploying production-grade ML systems across computer vision, NLP, and LLM-based applications. Without further ado, let me hand over the session to Mr. Ishara Niranjana. Sir, the virtual stage is yours.
Thank you, Shishant. So let me share my screen. Hope you can see my screen and hear me as well.
Yes, sir, you are audible.
Okay, thank you. So good evening, everyone. So today we are going to talk about AI on resource constrained devices. So the outline for the day is like we are looking into what is Edge AI, what is AIoT, and the cloud versus edge where the AI actually runs, and what are the constraints and design choices that we need to have on selecting devices, and Edge AI lifecycle. Then we will look into some of the tools and low-code platforms for building these Edge AI systems. And then finally, we will move on to the takeaways from the session and the Q&A. So let's move on to looking into what is Edge AI. So Edge AI is the process of running AI algorithms on the edge of the network or internet, right? So it is actually the processing at the source. So what is AI? So AI is the process that we are trying to mimic the human behavior and automate the processes the humans are doing. So if you look at Edge AI, so this in traditional cloud AI, so we can see that here we have sensors or some of the edge devices, and then we are sending this raw data into some sort of a cloud server. And then in these servers, we are doing this inferencing, and then the insights and the actions are given back to the device. So here in the Edge AI, we have these device that it is smart, so we can run these AI models on these devices. So we are doing the processing locally, not in the cloud server. So we generate these predictions or the results and the insights, and then we move those to the cloud storage. So we are only sending those insights and the actions to the cloud. And sometimes we may be at some logging in the device itself. And if you look at into the inferencing, so we have two separate inferencing processes. So we can do the inferencing in the cloud or in the edge. So in Edge AI, we are doing the inferencing in the edge. So if you look at these edge devices like smartphones, smartwatches, or mobile devices, and all these drones or industrial mechanics, robotic arms, likewise. So all these devices are edge devices. So we can run these algorithms on these specific edge devices, and we call it Edge AI. So now let's look into AIoT. So it is the combination of AI and IoT. So we have smart devices, fast decisions, and optimized operations. So it is about getting smart connected intelligence from these IoT devices. If you look at, according to the data of the International Data Corporation, so there are about 42 billion IoT devices in the world, and they are transmitting data over 200 million terabytes of data every day. So all these data we cannot handle in the cloud, or it is actually costly. So if we can process these into in edge devices, it will be more cost effective. For example, let's say you have a device in an industrial scenario, you have a robotic arm which is working on a, let's say, smart factory. So in that one, if you have a edge device, if you have built-in edge AI to this device, so if you now it is a robotic arm, so we can, let's say, we are seeing some mechanical issues in this robotic arm, and there are some vibrations or something like that. So if we have a edge AI in there, so we can identify this and predict that early, that there is issues in these mechanical devices, and then we can do the precautions way earlier than it causing trouble for the manufacturer, right? So we can build those systems with AIoT. So why edge AI matters? So if you look at into the main factors, it is the low latency. So we can get the immediate processing and the response from these edge AI. So if you look at the with cloud inferencing, or you are inferencing in a different server, so for the round trip on the network, it will take around 100 milliseconds or over than that. So you may have seen that with that, if you are running those inferencing in cloud, it will take some. So you are working with LLMs as well. So you can see that it will take some time, but we can reduce that if we are processing on the edge. And the second one is reduce bandwidth. So we are transmitting less data to the cloud. For example, let's say now we have some sort of camera, and we are processing those camera to some computer vision algorithm. So let's say we are identifying, counting the number of people or objects in from these cameras. And if you are not processing at this age, so if you are running this inference in a server, so you need to send these frames. Now let's say the camera is processing at 30 fps, so 30 frames per second. So you need to capture those 30 frames per second to do this inferencing, and you need to transmit this data, right? So if you are processing now, let's say for our algorithm, we don't need that. We need only about 5 fps to run our algorithm to get, let's say, 90% of accuracy. So in that case, if we want to only process about 5 fps, so we can do this processing at the edge device or camera itself and send the information to the server. So it will reduce the bandwidth as well. So and the better privacy. So if you look at into this aspect law, so now if you are looking into these, now let's get an example as the previous one, the computer vision application we are using. So we are looking into people, count people on these frames. Let's say we are doing that one. And so there could be some personally identified information as well. So we call it PII data. So in that case, if you are sending these over the network, there's a chance that there could be some malicious attacks in between. So if you are processing those at the edge, so data will be at the source. So we are not transmitting, so we are not sending the data over the network. So it will increase the privacy and the security. And it is working offline as well. So we don't need to have a constant internet. So sometimes if we want to do some sort of a model update or something like that, then we may have to do some, we have some internet, but most of the time we can work offline in these AGI systems. And the last one is, it is more energy efficient. So it will actually costing low power consumption on these devices. Now, if we look at, now we are reducing the bandwidth, we are not sending a lot of data over the network. And also, if you look at these data centers, in these data centers, they have massive cooling systems. So they are operating. So since we are not passing this data into those cloud servers or data centers, so since we are processing at the edge, these we are saving a lot of energy as well. And so this is about how AGI works. So the difference between training versus inference. So we are talking about low power resources. So most of the time we cannot train these models in these systems since we don't have enough memory and computing power. So we cannot train the model in those low power resources. But we can train these models in a server or in cloud, and then change these then we can reduce the footprint of these models and then deploy it in the edge device. So in the training process we have big data and complex models, and we can have high compute as well. So we can train a model, and when deploying we can convert these models into lightweight models and then do the inferencing in the edge. So we can get the real-time data, and then we can get the immediate insight and action on the edge device itself. So what are the key challenges in edge AI? So as I mentioned, we have limited computational power. So the forcing capability is inadequate for complex models. So we need to think on reducing the model size. And there are some techniques, and I will come back to those in a later slide as well. So from these techniques, we can reduce the footprint of the model and the memory constraints of the device. So when we are selecting the device, we can check on what sort of edge device we can need. But when you are looking into challenges in AGI, so the memory constraints is a key challenge, and the power consumption. So sometimes these AI tasks or the models drain batteries quickly. So it is reducing the operational lifespan of these systems. Okay, now when you are looking into selecting a device in AGI, so we need to identify the problem first. So sometimes we are selecting the devices and we are not identifying what is the exact problem we have to solve. And then so we need to check on the use case, whether it is related to analytics or forecasting. So some, if you are looking into some sort of a sensor data and some structured data, so the use case is belong to and do some predictions. So it is belong to analytics and forecasting. And if you are working with audio, so let's say sound classification or wake detection or voice to voice, some chats models, so it comes under audio processing. And if you're working with object detection, object tracking, or classification, and some work with the video, so it comes under vision and imaging. And if you are working with some navigation systems, control systems, or some industrial systems, so that comes under automotive and robotics. And then identifying after identifying the use case and what is the problem you are going to solve. The problem may be like you need real-time decision making, or sometimes you need to reduce the latency of this decision making. So according to the problem, then you have the use case. You need to identify which use case that you need to solve. So then you can select on a device. So selecting on the device, there are a lot of devices that you can look into according to your problem and the use case. You can go for some microcontrollers or some single board computers, or if it's for like use cases like vision and automated robotics, you can go for GPUs and NPUs and TPUs as well. So it is about selecting the device. And then, so when you are designing a solution, so there are some constraints that matter for these solutions. So it is about the interfaces. So whether you need Wi-Fi, Bluetooth, sensors, or a UI. So adding these specific interfaces actually adds more cost to your system. So you need to check on whether you specifically need these interfaces there, whether you need Wi-Fi or whether you need Bluetooth. So you need to decide on that one. And the power. So sometimes you may not get continuous power on the system. So you need to check on whether you need continuous power or you are running with the battery. So if you're running with the battery, you need to make sure that your systems are ready to some sort of a model, or the inferencing can go in sleep mode as well. So we are not draining these batteries when there are no actions happening, right? And then we need to think on the form factor. So whether how you are going to give this as a outputs, whether it is a large box or wearable or embedded one. So according to these ones, so you can decide on some decisions as well. Whether now if that is a very small one, so there is no enough room for some cooling systems as well. So you need to decide on what sort of a form your solution is in, and also the environment. So now, as in the previous example, let's say that we are looking into that robotic arm in an industrial process. So there are some vibrations, high noise, and temperatures. So your product or the system need to be can be run on these harsh conditions as well. So if it is indoor, there could be some harsh conditions, or if it is outdoor, so it should be water and dust proof as well. So you need to check on where these solutions are. You are going to build those solutions and where you are deploying those solutions. And according to that, you need to check on the design as well. And then the code portability versus optimization. So now if you are running these in low power resources, the code should be more complex because you need to do some constraints and you need to reduce the model size and you need to have a specific format to deploy these models in there. So these are some of the design constraints that we need to think on when we are building AGI systems. Okay. So these are some of the common AGI hardware options we have. So we have low-end MCUs with a RAM of less than 100 kilobytes. So it is more tiny and low power, and it is good for simple sensor-related tasks. And then we have some high-end microcontrollers as well. We have more memory, about some MBs, and we have different modules as well in these microcontrollers. So, and now you can see that these are increasing of computer power. The order is in the increasing of computer power. And then we have like MPUs. So these are general computing. So Raspberry Pis, and also there are some NVIDIA uh, Jetson series as well, where you can use these. And then we have GPUs and NPUs for heavier vision and AI models. So if you are running these complex computer vision related to audio related tasks, we need to go for GPUs or NPUs as well. So in NPUs, we have RAM about, we can go up to like 100 to 200 GB, but in GPUs, it is actually quite limited. So in that case, we need to connect those several GPUs parallelly and then use that VRAM to process these models. And NPUs are usually about few MBs, and it is actually more optimized for machine learning tasks. Okay. So these are some of the options we have when you are looking into deploy these models or AI models in several hardwares. Okay. Now we have talked about what is AGI and some of the decisions that you need to make when you are selecting a device, and also some of the options we have for device. And then we need to think on building these entire end-to-end pipeline, right? So in machine learning, we have several processes that to get a more accurate model. So for example, this is the entire pipeline. So here, if we look at, we have some sort of a raw data. So in this case, the data comes from sensors or maybe your IoT device or the system, right? So we have this raw data, and then we need to go for data cleaning processes. So usually in data science or AI and machine learning tasks, we need to do this data cleaning, because sometimes there may be wrong information in the data, or there may be some duplicates or missing values as well. So in these, so in order to improve the accuracy of these models, we need to do some data cleaning, and then in that process we can do some data visualization as well to see whether there are some patterns as well in this data cleaning process. And then we have feature extraction and engineering processes. So here, this step, we need this step because now let's say we have some 100 variables or 100, we are getting data from 100 sensors or something like that. But to your end goal, so if you are making a prediction, we might not need these all 100 variables. And also, if you don't have enough data, adding these y variables, so the dependent variables will be the independent variables will be reducing the accuracy as well. So we call it curse of dimensionality. So when the dimensionality is high, we need a lot of data. If not, our models will not perform well. So we need to do some feature selection and extraction, and sometimes we need to do some feature engineering as well. So we can decide on that whether we need some feature engineering according to our use case and the results of our initial training models. And then we can select a model or an algorithm that train on this data to do some predictions, and then we have a model. So in that case, when you are selecting a model, so it is better to have a simple model. So we don't need to go for complex models all the time. So if the use case is very simple, so you can get the most simpler model. So you can interpret these models easier as well. So when the models are more complex, we cannot interpret these results, and it is harder to interpret. And so we can start with some basic statistical models, and then go for some machine learning models. And if it is not working well with these models, then we can go for some deep learning based models as well. And then we need to do the model testing. So in the initial data stage, we need to divide this data into mainly into three parts, but sometimes we are make dividing it into two parts as well, training and testing. But it is better to have training, testing, and validation set as well. So then from this testing data set, we need to check the model accuracies. So we need to have several algorithms running, and then from these algorithms, we are getting the accuracy. And then we can identify the best algorithm or the best machine learning model for your specific use case. And then most of the time we are directly do the deployment. And then after the now from the historical data, you have a good model, and let's say you have more than 90% accuracy and all good, and you are going to deploy this model. And then after that, most of us think that it is the end of this machine learning pipeline. But after the deployment, there could be changes into the data, and the model performance could degrade over the time. So we need to have some sort of a monitoring process as well to see whether your model is working well with the new data. And also deploying the model, most of the time we are not thinking of reducing the model size, because we have trained the model on trained data set, and we see that the accuracy is good, so we are directly deploying that model. But in this, before deployment, you can check on whether you need these every connection, so whether you can reduce the parameters. Likewise, you can check on whether you can reduce the size of these models before deployment as well, so it will save the cost as well. And so this is the end-to-end pipeline. So from a, let's say from IoT device, IoT system, we have the raw data, and then to get the model, we need to go on this specific process to get the good model accurately working for predictions. And then I mentioned that we need to check on monitoring, right? So in this case, the model drift. Model drift happens due to the concept drifts or the data drifts. So, for example, let's say we have a computer vision algorithm running on camera frames, and then if the brightness or the place or the angle of the camera changes, the data input data changes as well. So due to that, the results could not be great after deployment of this model. So we need, that is an example of data drift. And also there could be happen some concept drifts as well. For example, let's say we have a simple algorithm on house price prediction, and the house prices have been increases due to some let's say some construction happening. So there could be a new highway around that area, or some sort of a building on that area. Due to that, the prices of these lands are being high. So in that case, the historical data doesn't have these patterns. So the model trains on those historical data, but now the concept has been changed. The mapping or the function between these inputs to output has been changed. So due to that, your model will not perform well. On the new data. So it is what we call model drift. So in the model drift happen due to these two steps, like from data drift or the concept drift. And then, so to identify these model drifts, we need to have continuous monitoring. So on new data, we are checking whether our models are working well and we have enough accuracy. So now let's say, for example, for that computation algorithm, we need to have around 90% accuracy. So if it is over 90, it is fine. But if it is going less than 80, we need to do a retraining on these models. So likewise, we need to have a threshold and check on whether these models are working uh, or the accuracy is over that threshold. And if it is degrading, then we need to have some retraining process. So we need to collect that new data and the historical data, and then train a model on this data and check the accuracy with it. And so in that case, the model might change as well. So the algorithm could also change, or some parameters, high parameters could change. And then we need to check the accuracy of this model. And if the accuracy is good, then we can redeploy this new version of the model. So we have this system. After deployment, we are checking continuously for the accuracy. And if the accuracy drops, we are doing a retraining process. Likewise, this is some iterative process to check and maintain the accuracy of our system. Okay, so this process we call as MLOps, or ML operations. So it is the process of automating this data collection, training, and the deployment and monitoring process. So in edge systems or edge AI systems, it is actually hard to do this monitoring process and the deployment. So we need to deploy these models over there. So for example, let's say for your watch or the mobile phone, so there are updates coming, and usually the models these devices are checking on updates. And if there are model updates, you can download these updates into your system. So there are thousands of devices, so we cannot manually deploy these models. So in that case, we need to have a mechanism to check whether there are updates to your system or the models. And then if there are updates, we can download these updates and then run on the device. And also then we need to have separate data versioning as well for these systems. So in that case, we know that these specific models are built on these specific data. So if there are any issues, then we can check and identify those things. So in HMS MLOps also, we are automating this process of data collecting, training, deployment, and maintenance. And we need to have this cycle to have more reliable systems. Okay, so these are the core concepts in Edge MLOps. So it is about version control. Here we are checking the work and track the changes for the code, data, and models as well. So as I mentioned, we need the data version is very important, because we have to have some sort of version mechanism for data, so we know that these specific models or the accuracy of these models we got from these specific data sets, right? And also these models. And then about the automation, so it is about now we need to automate these model training processes, deployments, as I mentioned. So if you want to deploy these model updates into thousands of devices, we need to have automated system, and also the monitoring and give the updates. So if there are any issues on these systems, version control and automation, so we have the ability to roll back for previous systems as well. So if there are any issues with new updates, we can directly roll back into previous versions as well. And about the governance, it is about maintain ethical phase of these models. So we need to have you unbiased results as well. So we need to check on those things. And also we need to ensure the compliance, fairness, and security and data standards as well. So as I mentioned previously, when we are doing or when we have AI AI systems and in the edge, so in that case, since the data is there, it is more secure, and we have more privacy on the data, since we are not passing those data. But we need to make sure that the data we are passing those, so we are passing those insights to actions for servers to store. So in that case, we need to make sure that if we are sending anything out, that those are compliance to the data standards. Okay. So now we talked about those devices and the processes of training a model and deploying, and after deploying, we need to monitor those systems as well. But when we are training a model, so how we make these models tiny? So we may have heard a term called tiny ML as well. So it is about machine learning. When we are doing machine learning tasks on low resource, raw compute power resources, so we call it tiny ML. So it is a subset of edge AI actually. So there are a few options that we can do to reduce the size of the model footprint. So the first one is quantization. So you may have heard about this term. So it is about reducing the precision of these parameters. So uh, most of the time we are using these, we are reducing the precision from float 16 to float 32 to float 16 or float 32 int 8. So I will show you some example how we can do this one. And if you want to learn more about model quantization, you can go into these links as well. So this is from Hugging Face. So in this case, we have some algorithms like to quantize these precision. So it is actually quite easy to quantize between float 32 to float 8, float 16, but it is sometimes harder to change that to float 32 to int 8. But we can do these conversions, and when you are doing these quantizations, still there could be some quantization error as well. So after the quantization, the accuracy will not be the uh, there's a chance that accuracy will be less than the original model. But according to the use case or the device we have to deploy model, we have to do these processes. So we have these algorithms and all the steps that we can do for quantization. So I will share these links as well, so you can check on how to do this quantization process correctly. And then we have model pruning. So here what we are doing is, now let's say we have a neural network, and most of the time, so all these edges, we are not needing these for the accuracy. So we are actually zeroing out those some of these parameters. So we call it pruning. So we are actually reducing the number of edges in a neural network, or the number of connections. And we can use some small architectures as well, for example mobile net, or some sort of a simple statistical models as well. So if you look at post classification, there are small statistical models as well, like projection regression and decision tree classifiers, random post classifiers. So in that case, we can try on that whether it is better to use some smaller models like why. And looking into feature engineering, so it is actually very important one. So we talked it about in the machine learning pipeline as well. So we can reduce the model size from reducing the features as well. So we need to identify the most important features and do a feature selection and to reduce the model size. And then we have knowledge distillation. So this is the process of training a student model to mimic the behavior of the teacher model. So we have two models called teacher model and the student model. So the student model is trying to predict the output layers of the teacher model. So in that case, we are reducing the layers to get the accuracy of the teacher model. So there's another good article on this one about how to do the knowledge distillation. So yeah, so this is also from the Hugging Face. So here there are some details about how we can do the knowledge distribution. So this is a step I mentioned. We have the teacher model. This is trained on the entire data set, and we are transferring these teacher models learnings to the student model. So in this case, we are trying to predict the some layers of the output of different layers from the. Now, for example, let's say in the teacher model from layer 1 to layer 5, uh, we in the inputs to the layer 1 and from the output to the layer 5, So what we are doing is we are matching this input for layer 1 and layer 5 and train a model to do that one on single layer on the student model. So that is what happening in knowledge distillation. So if you want to learn more about how this is happening and to look more into this knowledge distillation, you can refer to these links as well. So this is actually from Hugging Face. So there are some multi-teacher distillation, like there are some different versions of this knowledge distillation as well. So you can look into that one. Okay. So it is about how we can reduce the size of the models. So these are the techniques we have. And also if you look at there are some quantization method for LLM, reducing size of the LLMs as well. So you may have dual or Q lower as well. So those are also some quantization options we have. Okay, so now let's move on to some HGI platforms. So one of them is Edge Impulse. So these are some of the three options we found. So here from Edge Impulse, so it is we have the end-to-end development platform. So from data collection to model deployment. So you can data from sensors and you can mimic those behaviors in Edge Impulse as well and do the deployment. And then we have Arduino. So it is actually it is use hardware and software. So and in Arduino, we have a large community and ecosystem. So which actually supports TinyML libraries as well. So it separates Java TinyML kit in Arduino. So you can do some experiments on these devices. And then we have STM32 Cube. So it is actually optimized for STM32 microcontrollers. And this code generation, it supports code generation for these embedded devices to specifically for these microcontrollers. And then we have some AGI frameworks. These are the ones usually we are using. So one of them is TensorLite. So it is optimized for mobile and embedded devices, and it has wide support. And now it is called Light RT as well. So you can go into these documentations and see how you can change your models so into different formats. So if you want to deploy the models in an edge device, you need to convert this into Light framework. So you can go to PF Lite. It is one of the frameworks. And then we have PyTorch Mobile. Actually, now it is the name is changing to Execute Torch. So they are not supporting PyTorch Mobile now. So it is the capability on this PyTorch Mobile is now on Execute Torch, and it is you can use for the deployment on iOS and Android Linux platforms as well. And yeah, they have a good documentation on how to use these on different devices. And then we have Onyx. So it is actually a prospect. It's actually a model format. So if you build a model on TensorFlow, Torch, or Keras or something like that, and then you can convert this model into Onyx formats, and then these Onyx formats are running. We can run those models in different platforms. And in Onyx also, they are doing some sort of a quantization. So due to that, the accuracy of we need to check on the Onyx converter model that the Onyx format models may be performing less than the original model because they are doing some quantization. And now we talked about most of the time about these low power resources devices and how to do deploy models on these devices as well. Now we know that there's a lot of hype on generative AI at this moment, and there are some devices that you can run LLMs locally as well. So this is a device from NVIDIA called DJ Spark. So in that one, you can run those LLMs locally as well. So this actually support more large models. So actually in your laptops or some devices, we can run some models, simple models of some small LLMs, but this supports larger models as well. So let's see an example on this specific device, how it is performing, and an example of a use case that they have been shown.
Let's build a personal assistant. I want it to help me with my calendar, emails, to-do lists, and even keep an eye on my home. I use Brev to turn my DGX Spark into a personal cloud. So I can use the same interface whether I'm using a cloud GPU or a DGX Spark. I use a Frontier Model API to easily get started. I wanted to help me with my emails, so I create an email tool for my agent to call. I want my emails to stay private, so I'll add an open model that's running locally on the Spark. Now for any job, I want the agent to use the right model for the right task, so I'll use an intent-based model router. This way, prompts that need email will stay on my Spark, and everything else can call the Frontier model. I want my assistant to interact with my world, so I'll hook it up to Hugging Face's Reachy mini robot. My agent controls the head, ears, and camera of the Reachy with tool calls. I want to give Reachy a voice, and I really like 11 Labs, so I'll hook up their API.
Hi, I'm Reachy, running on DGX Spark.
Hey Reachy, what's on my to-do list today?
Your to-do list today. Grab groceries, eggs, milk, butter, and send Jensen the new script.
Okay, let's send Jensen that update. Tell him we'll have it for him by the end of the day.
Will do.
Reachy, there's a sketch too. Can you turn it into an architectural rendering?
Sure.
Nice. Now make a video and show me around the room.
Here you go.
That's great. With Brev, I can share access to my Spark and Reachy, so I'm going to share it with Anna.
Hey Richie, what's Potato up to?
He's on the couch. I remember you don't like this. I'll tell him to get off. Potato, off the couch.
With all the progress in open source, it's incredible to see what you can build. I'd love to see what you create.
So in this one, you can see that this LLM is also locally deployed for privacy concerns or some sort of, so about those things. So you can deploy these LLMs locally, and it is actually the LLM is running at the edge. Okay, so now this is an example of from Edge Impulse to end-to-end pipeline about a simple deployment. So we'll quickly go into that one as well. Yeah. So this is a tutorial from Edge Impulse. So here you can see now we connect the mobile device so into this platform, and after connecting we can get the data from the device. So in this case they are trying to connect the mobile phone and then get the data, and what they are doing is like they are collecting data to identify the pattern of the motion of the mobile phone. So they are collecting data for idle, snake, wave, these different patterns. So likewise then they are collecting the data set and then design an inference on the Edge Impulse, and then in this platform itself you can train a model. So this is an example of the hyperparameters and the model that they have running on this platform. And then so this is about also the results of this model training process, and you can configure neural networks or any other models as well and check the accuracy of these models and see how it is working with new data. And then also you can deploy this model from this platform as well. So there are some tutorials as well. So when you have time, you can check on these tutorials and try to do some implementation using these platforms. Okay. So now I will quickly move on to another case study from them. So this is about they are going to do some AGI system to power grid. So they can check the condition of these power grid systems. So let's see how they have been built, these AGI systems and the importance of it.
Recently partnered with Electron, near us, to bring intelligence to the smart grid. By putting smart sensors on the top of each power pole, we're able to monitor what's happening in the power lines in real time.
The system of discovering faults right now on the electricity network is a very old-fashioned way.
The combination of sensors in round one enables to early detect all the faults on the electrical grid. Particularly of interest are the ones that can cause sparking and various effects, which could lead to a fire, for example.
The device can influence a lot on the public safety because our device will notify about the fire before the major fire happens.
Now, this has a huge impact. For example, forest fires here in California are a major disaster each year, and this kind of technology can help prevent it.
It has two important things. So firstly, it's a very electrical grid focused approach, which means it brings something fresh and new to this industry, which is very traditional. And a lot of the equipment on the electrical power lines are actually 20 or 30 years old. Our mission is creating advanced applied systems, meaning we take existing technology, existing solutions, and create something new and novel from that.
Motivation for collaboration with Edge Impulse is machine learning ability that our device have.
This is the Edge Impulse part here, because it allows us to have, say, a basic notion of what these devices do out there at the moment. With all the inputs and with more devices in the field, they can become much smarter as they grow, as they mature. So Edge Impulse is very good in enabling you to do things in whichever field you are. So we would definitely motivate companies to try out Edge Impulse, to try to put it in their product, so they'll see how good of an experience that actually is. It's the best thing that is out there to put machine learning into an embedded system.
Yeah. So this is actually a real world example. So they have deployed that advanced grid monitoring system to work in Edge. Okay, so now let's look into some of the key takeaways from this session on Edge AI. So we look into what is Edge AI. It is about getting the intelligence closer into these devices. And then in the edge devices, it is actually, we can get the insights of the results of the actions more fast. And so it is more, it is more efficient and also cost effective. And we talk about the constraints that shape models and also the devices that we need to look into and the design decisions that we need to take on the use case as well. And also when we are deploying models, we need to check on the model optimization side as well. So from optimized models, we can get better results. And also also we are using less power to run these inferencing on these models as well. And then there are some platforms that simplify this end-to-end process of deploying these models. So, and also there are some frameworks as well to support these Edge AI devices. And then finally, we need to start small and then iterate on these specific versions of these models and also the systems. And then later we can scale up our systems. So we need to build step by step. Yeah, so those are the things I had to talk about Edge AI and on these real world applications on Edge AI. So now I will move on to the questions that you have, and let me check whether you have any questions. Yeah. So at this moment, I am not seeing any open questions. So if you have any questions, you can add those questions as well. Yeah, I think the first question is for the organizing committee. So I think the organizing committee will get back to you on that one, Siddharth. Yeah, there's a question like, is generative AI even possible at the edge, given the resource constraints you have discussed? Yes. So I discussed about some of the resource constraints, but when you're looking at the edge devices, so there are different edge devices, like so from microcontrollers to Arduino, and also for about there are some GPU powered edge devices as well from NVIDIA. So on those edge devices, you can run some complex models as well. So we can do some generative tasks in edge as well. For example, the video I showed, in that one we have NVIDIA DGX Spark. So in that one, we can run models up to some about few hundred billions parameter models as well. What are the other platforms that we have to use to train an AI model to detect objects, face recognition, movement tracking, like things? So most of the time, simply you can build a neural network on framework using frameworks like TensorFlow, Torch, Keras as well. And then to deploy these into edge devices, you can convert these models. So in that case, you can use a format like TF-Lite or Onyx. So you can convert these models built on TensorFlow or Torch, and then convert these models into formats that are working on edge. So apart from edge impasse, you can directly use these frameworks and do this processing and training of these models and then deploy. So you can use those as well. Yeah. So the next question is, how do we balance the performance and space efficiency of the ML model? So this is actually depend on your use case. So sometimes now, according to the complexity of your use case, we can check on. So it is actually a trade-off between the accuracy and the model size. So when you are reducing the model size, the accuracy will degrade. But let's say for your use case, you need only about 80% accuracy, and you don't need over 90 accuracy. So in that case, we can reduce the model size, and we can make the system up to the standard we want, sacrificing the accuracy. And so we have a low footprint model, so the cost and the efficiency will be high. Yes. Is there any AIT deployed in Israel, and if so, can you give some examples and the company doing it? So actually, I cannot give the exact company names here, but there are some companies who are working on agri-tech. So they are doing those AIT deployments most of the time. So there are some other companies as well, but I know that there are some companies in agri-tech that they are doing these AIT deployment in Sri Lanka as well. Yeah. So the next question about Arduino IoT to build with custom hardware. So actually, I'm not sure about that question. So I need to check on that one, and yeah, I will try to get back with the organizing committee on that one. Yeah. What can we do about the high hardware cost for these devices? What can we do about the high hardware cost these devices? So yeah, so if you look at these simple microcontrollers or Arduino boards, so it is actually not the cost is not much high. But if you are going for like these NVIDIA devices, the cost is somewhat high. So what we can do is trying to reduce the model complexity and do the deployment on the model. So when you are training the model to identify the model that we can use for our use case. Okay. There are some questions related to the competition, I think the organizing committee will give you an answer on that one later. Yeah. There's another question from AI model that answers any question of the user like a chatbot regarding any specific topic. Is there any platform to train an AI model? Yeah. So in this case, we can do a fine tuning of a model. So because train a model from scratch for some sort of a LLM based task or a general chatbot related task, it will be much and we don't have enough data to train that sort of model. So we can go for a simple models like BERT models and try whether these versions are capable of doing that one, or we can do a fine tuning of a simple a small LLM on platforms like there are many cloud platforms that are supporting these retraining processes or fine tuning processes. So all the platforms like Google Cloud and Azure and from Google Vertex AI, from Azure Machine Learning and AWS SageMaker, they all support these fine tuning of these models, the LLMs as well. So you can use these platforms. Okay. So I will ask few more questions since we ran out of the time, and if there are more questions, I will get back to you on those from the organizing committee as well. So the next question is there any platform to do the complete IoT simulation of our project which can handle ML models as well? Yes, there are some platforms from Google that we can use for this sort of a simulation as well. And there are few other platforms as well, but actually I couldn't exactly remember the name, but there are platforms you can do these simulations. So there's another question like, can we use commercial softwares like IoT or to build with custom hardwares? Blink IoT to build with custom hardware to make our project. Will it disqualified because of using commercial ready to use softwares? So I think organizing committee will get back to you on that answer. Okay. So those are the questions we have. This, and I think I covered all the questions. Yeah. So if you have any more questions, you can raise it to the organizing committee as well. So I will get back to you on these answers. And thank you for joining and listening as well.
Thank you very much, Mr. Ishara, for that insightful presentation. As we near the end of this program, I would like to invite the Vice Chairperson of the SLIT Challenge 2026, Mr. Yasir Bandara, to deliver the vote of thanks.
So I would like to sincerely thanks on 24/7 for their incredible support and for hosting the SLIT Challenge 2026 technical workshops, empowering our participants with valuable industry-level guidance. Also, a special note of appreciation goes to our guest speaker, Mr. Ishara Neranjana, and our academic advisor, Dr. Kutila, and the SLIT organizing committee and the SLIT delegates, and everyone who supported and contributed to making today's session a success. So also following today's session, you will have one more upcoming session in the coming week on the 9th January. We will conduct a how to market your product workshop. Also, we strongly encourage all team to make full of use these opportunities and finalize your project proposals before the deadline. A large number of teams have already registered. This is your opportunity to refine your ideas and emerge as future leaders in the IoT industry. So as mentioned earlier, this is not just another competition, it is a platform that can truly shape your future. So the SLIOT Challenge 2026, organized by the Department of Computer Science and Engineering, University of Moratuwa, in collaboration with SLT Mobitel and IESL, is designed to empower and elevate you. So once again, thank you to everyone for being part of this journey, and have a great night.
This concludes our second session for the SLIT Challenge 2026. We hope to see you all on the 29th, where we will explore the entrepreneurial aspects of creating an IoT product. We encourage you to make use of these workshops and apply them effectively in the competition. With that, we come to the conclusion of today's session. Thank you for joining us. Good luck to you all. Signing off, I'm Prabhaharan Sheshanth.